Okay, so finally, last section. Let's finish. So last section, we want to touch some subject a little by little. So today, at this section, I will touch a little bit about the linear model and correlation, and then Lauren talk about some different type of extension what we can do in R. So this is the our the summary file in the Dropbox. So I want to show this one of the example. It's a very famous example as a motivation. So this data set have 1, 2, 4. They have 4 combination of this. So here's the x1 and y1 paired, and then another combination set x2 and y2, and another combination x3, y3, x4, y4, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 measurements for each combination. And then based on this, we actually calculate the very basic summary what we commonly do. So here, we calculate the mean and variance for x1, mean and variance for x2, x3, and x4. And then here also same thing, variance and mean for y1, y2, and y3, and y4. And then last we calculate the correlation between x1, y1, x2, y2, x3, y3, and x4, y4. As you can see, actually the data looks quite different. However, all the summary values is exactly the same. 4 different cases, right? So here correlation looks everything is good, like so more than 80%, and actually they have exactly the same mean and variance. So actually I tried to look at this original value, how it look like, and then it is like this. So first, x1 and y1 combination is this. And then here's x2 and y2 combination. They have some curved shape. And then here, they have x3, y3. They actually have linear. However, they have one huge outlier here. And then here, actually, not linear and not curved at all, just the same x value, and then one huge outlier. However, 4 different cases, actually the summary is about the same, especially the correlation, right? But usually we just put the correlation, it's just 90% or 80%, but it can be like this case, right? Can you tell this is really correlated? No, right? So I think so 2 things I want to address. First one, don't believe too much about the correlation. And then you always need to double check how data look like before you are doing any calculations. So that's why the visualization is very important. Visualization for summarize the statistics also very important to report to show your result, right? However, for before you start to any data analysis, it's very important to check the data first. So most likely, when I have a more experience, actually I spend more and more time to look at the data first, and then pre-processing and filtering and just find the issue, and then rest of them maybe can be the more straightforward. So this is the cases. So that is what I want to address one. But be careful. But let's try to make how we can make the correlation plot. So I will just show the very short examples. So let's go to our IPRG data again. So before that, I will call the library tidyverse because I want to use one of the functions to modify our data. So let's call tidyverse. tidy R. And then let's modify a little bit. So let's just review how original our IPRG data look like. As I remember, IPRG data is a data frame and then several columns which include the different informations, right? So each column have a different information one. However, I want to use first 3 column only and then make a little bit changes. The first 3 column include the protein ID and log to intensity and the run information we have. So I want to make another data IPRG2 is we want to spread IPRG data of column 1 to 3 only. Spread by run, and then I put the value log to intensity in there. Then how it look like IPRG2. Now still, so this one have each column have by each run, and each row is by the proteins. And let's check the column name of IPRG2. Column names here as so as we can see, column we have a protein column, and then other one is by each run. So first what I'm gonna do, I will move this protein column to row names, and then I will use first this 3 run because it came from sample 1, and then it included the spread. So I want to see from the same condition if you have a replicate how they correlate between the replicate. So first I will change row names of IPRG to I want to put the log to row name is IPRG2 proteins. After that, I can remove this protein column, IPRG2, and then I will move first column. Okay, then IPRG2. I check the dimension of IPRG2. Oh, yes, I just, now we have 12 columns, and then more than 3,000 rows. This is by each protein. Then I will subtract first 3 columns. So let's say this is just X. X should be IPRG2 in the first 3 columns. Now let's check the dimension of X. Same number of rows, but now we have only 3 columns. So that is 3 columns came from sample 1 and then with different replicate. So to draw the correlation plot, we can use pairs function and x. Here it shows correlation between these two runs here, here, and these two here and here. So we can see there are some outliers, and then if around the row intensity, we can see they have the more variation here. And this is just plot, but I want to see actual value. What is the correlation value, right? In that case, we can use core x But here, now, I can see there are so many NAs because some of the intensity value actually NA, so they cannot calculate with NA, right? NA plus 1 is actually NA, not 1. So in that case, we have to remove NA first. So what I can do here, x2, let's omit NA from x. Then now I can see here x data have 30,028 objects, but x2 we have 30,026 objects. So because of the only one NA value, actually we have a NA value for everywhere. Then let's calculate the correlation again for x2. Then now we can see this correlation value here. Okay, and as I show one of the example at the beginning of this section, so correlation is really hard to say. It's really what we want to address. So for another way, we can show this type of the correlation between the replicate. We can draw the MA plot. So people actually from genomics area probably is very familiar with this MA plot. So MA plot means plot. We're gonna draw the plot. A means average, and then here M means difference. So for example, if you want to check the correlation between A and B, this is just average of this A and B, and then this is just difference. How it look like is actually the correlation plot look like this way. However, this means we actually change this coordinate like this way, here and here. Then if we have some outlier, we can actually see how much is far from this x-axis and so on. So let's try to calculate this. So I want to make a MA plot for first A and B. So let's put the R1 is the first column of x2, which is actually A, replicate. And R2 is from replicate B. Then we can just calculate the m value here. I said just difference, right? So difference between two is R1 minus R2. And A value is average between these two. So R1 plus R2 and divide by 2. So let's calculate this M and A here. Then simply I can use plot functions. A, M. So for plot function, first one is x-axis, second one is y-axis. So when I run this, it shows this plot, which means we can easily see how much actually they have a variation. So here, if we see some outlier, we can see some outlier here, and other thing is very close to here. So this is our MA plot. And also with this to replicate, we can do also make a linear regression one. For linear model, we can use LM functions. So I want to calculate the linear model between R2 and R1. So R1, R2 is, R1 is for replicate A for condition 1. R2 is replicate B from condition 1. So we want to check the linearity between the two replicate A and B. And let's run. When we run this, it shows very short summary of this. But as what we practice with the t-test, let's save this result. So result LM. Then the result LM will include all result or final numbers for linear model. Then summary function will show more detailed information about the result. So here it showed the first they call calls what function I defined it, and then showed about the residual values, and then show coefficient, and then for each coefficient what is the estimate and what is the standard error, and t-test and p-value, and so on. Right? This is just show the summary of the result. However, if you want to extract each value, you can also check names, result, LM, and then it shows how you can, what kind of the another value you can extract from result LM. So this is the same as what we practice with the t-test part. Okay. Then we can actually plot these two things. So plot R1 and R2. Show this. And then I want to plot our linear model, overlay this plot. Then we can just here, I said, I want to add line from our result LM. I want to make this one is more visible. So I want to change this color. Then they just add the line here. So this is our finished the linear model, and then this is our original values. go back to row names. Row names. Row name of what? Which data set? So we actually, this extract go out. So this is just a simple list of the linear model functionality. So if you have very specific model you want to check it, please stop by us, and then I will just toss this one to Lauren, and then he will touch the last content we want to cover. Okay?
So before carrying on with what we have on schedule, I just wanted to come back to group by from dplyr, because there was a question on one of the sticky notes, and I wanted to clarify something here. If we say group by condition, and then let me write this down here. Then the example we had was summarize mean intensity equals mean So that was one, and that was an example. And I wanted to clarify that. So coming back to my drawing from last time, what we observe here is indeed the mean. This is intensity. The mean of all these intensities. The mean of all these intensities. Same thing for all the here, all the here, all these intensities. To calculate, irrespective of their order. The way I drew them here is all the ones that includes these forms. Irrespective of the order, this is what is going to happen here. And so we could try to check this, of course. If I say IPRG filter condition equals condition 1. Okay. I select all those that have condition equals 1, and then select intensity. Intense. Oh yeah, oh my god. No. Okay, names. Can you help me? I need to quote? I don't think so. Yes. Why is that? Well, this is because there are different packages that define a function select. If I type the name of a function, oh yeah, I know one. If I type the name of a function, I see its code. So for example, ls is also redefined somewhere else. If I type select, I see the code of the function. It's a special type of function here, and I also know what package this comes from. So if any one of you types select, they will see something else. They will not see this code. They will see a select function that comes from dplyr. Am I correct? Yes? Because during the break, I came and installed and loaded a couple of packages here, so I was sure they would be installed and they would work for the second part of my presentation. I loaded other packages, including an annotation DBI package that also defines a function select. So if I type select now, the first one that is found by R is this one, but that's not the one I need to use. I want to use the function select from dplyr, so I have to specify it like this. Okay. So when different packages define the same function, the same function, by that I mean the function with the same name, that is exactly like if you have the same file name in different directories. There is nothing wrong with that. The only thing is that if you specify that file name, you need to make sure that you refer to the right directory. It's the same thing that happens here. So temp. So here I have all the intensities for condition 1. And if I calculate the mean here, this is what I get. Let me recalculate this. It's correct. Okay. So here I have calculated this manually, but by using group by, all this happens automatically. Okay. And by doing things manually here, lots of bad things can happen, a typo. So group by is very useful. But I also wanted to show you that I can also group by multiple conditions. And again, irrespective of their order, dplyr, the group by from dplyr will identify all these categories and then create sub-data frames and calculate the summary statistic I want. So I hope that this clarification answered the question for on the sticky note. Okay, so we have two last topics to cover before. Is it 5 or 6? 5. Okay. Yes. And so one of them is to give you an idea of other software that can be used, specifically software that is designed specifically for mass spectrometry or proteomics. And these software would generally be found in a project called Bioconductor that I think I already mentioned. And if you don't know, if you have a vague idea of what you're looking for, but you don't know, you're not familiar with the project, you don't know the name of the package, it can be difficult to identify among the 1,560 packages on Bioconductor which one would be helpful. But Bioconductor, as opposed to CRAN, for example, has specific tags that come or that are used to label different packages that help you to kind of search with these tags, with these keywords. So if you click on the link here, software packages, you end up on this page and this classification for all the packages that are available in Bioconductor. And so, for example, if you're interested in proteomics, you can use one of these proteomics. They're called BioC views. And this now lists here all the packages that are tagged as being useful for proteomics. Now, this can be loosely related to proteomics or fully kind of meant to be used with proteomics data. But at least they have all these packages. I don't know if they say how many there are. Here, 105 packages that are tagged with proteomics. There is another tag of interest here, would be mass spectrometry. So 70 packages that are tagged with mass spectrometry. So if that's something that's interesting, that would be kind of the first way to identify those that are interesting. And of course, some that are tagged with mass spectrometry you will also find in proteomics. So what I'm going to do is back. I'm going to copy that URL here in my script. That will be made available. So all the scripts, all the projects will be made available on the Google Drive. Yes? Yes. Well, actually, so I'll afterwards add another link where I describe a little bit how to get started. So one way would be if you find a paper of interest and they mention the package or an analysis they have done, and they mention a package, that is maybe one good way to go and find exactly the package that you're interested in. Going through the BioC views, these tags are useful. Something else that can be helpful is that on the Bioconductor page, in help, where is it? They have a workflows page. And let's look at the release workflows. No. So help. Oh, they have a problem with their, oh no, workflows here. So, it's the same page, that is new. So the workflows are kind of extended documents that describe what can be done with some of these packages for a domain of interest. So for example, if we look at the proteomics workflows here, we have two packages, one that describes high throughput assays and the other one proteomics. And on the right hand side here, mass spectrometry and proteomics data analysis. So clicking here provides more links. No. Sorry, the page has changed. It did not used to be like that. I'll add the link. So these are kind of workflows that describe multiple packages that can be used for that domain. That would be also one way forward. Something else that is useful is if there is a package of interest. Every Bioconductor package comes with what are called vignettes. So, for example, the Msnbase package that I want to show later comes with this relatively long. Oh, sorry, I didn't want to show this one. This documentation about the package that provides a general overview. So not the documentation about the functions that I showed yesterday or the day before, which is very technical, and you need to know what you're looking for. But these are kind of a large overview of what can be done with the package. And maybe the last thing that you could do is to ask a question on the Bioconductor support forum. I'm trying to do this analysis. Does anyone know a package that could do it? So here are the packages that I will need for a short demonstration. So I would like to show 2 or 3 things. And focusing, one of these is focusing on how to read mass spectrometry data into R. And so and proteomics data, when I talk about proteomics data, I think of raw data, that would be my mass spectrometry data. I could also be interested in identification data, or interested in quantitation data. When we talk about raw data, the file format that this comes in would be MZML or MZXML, or one of these open formats that are available. So this would not work with your binary, the proprietary binary formats that are produced by the instruments. You need special libraries for this. But all the open formats that can be generated by MS Convert, for example, would work here. For identification, they also have such a format, which is MZ-IdentML. And for quantitation, typically, the formats that have been developed by the communities are either MZ-Tab or otherwise spreadsheet. And use Project Discoverer, MaxQuant, probably any piece of software will allow you to export a table, protein, samples, and probably additional annotation into a CSV file or similar. And so once you have these, and if you want to read these into R, there are a couple of functions to do that. Here we have read MS data. This is the function that will load an MZML file. And it will create an MS and X experiment with MS data. So this is a little bit like we have some data frames and vectors, but these are special data structures that will allow you to kind of manipulate raw mass spectrometry data. For identification data, there is a read MZ IdentML. Data. And this function will produce a data frame. So already very functional. So if you have one of these files and you want to, which are XML, they are a little bit ugly, we can read them into R as a data frame. And then use dplyr and ggplot to analyze them, or to visualize them, or to parse them. Finally, are you familiar with MZ-Tab? Is anyone familiar with MZ-Tab? Hasn't taken on if you have a spreadsheet with quantitative data as produced by MaxQuant, Project Discoverer, and so on, there is a generic function called read MSN set. It's also a read MSN set, but the version 2 is easier to use. We'll read that spreadsheet for you and create an MSN set object. It's a type of object that is dedicated. It knows that your quantitative data here contains quantitative projects. So to demonstrate very briefly this one and that one, to give you an idea of what kind of things can be done. Yes?
Is that data built for what version of R? I'm getting that it's not available for 3.4.
Okay, so thank you for pointing this out. These packages live on Bioconductor. So you can't use install.packages to. Thank you, that's actually something I wanted to say. So to get started with installing Bioconductor package, you'll need to type this only once. Now it tells me that it's using Bioconductor 3.7 because it's already installed. If it was not installed, the first time I run this in a computer, it would install a package called BioC installer. And once you have BioC installer, you can say BioC Lite, and then the name of a package, for example, and then it will install that package for you from Bioconductor. Now the reason it is a little bit different and install package doesn't work is because there is a strict relation between the version of R and the version of Bioconductor. Okay? That's not the case with CRAN, the kind of general R mirrors. You can, whatever the version of R you have, you will get the latest version of the package. With Bioconductor, there is kind of more structure in the project, and for one specific version of R, you get one specific version of R packages. But in addition to that, BioC-Lite also works for CRAN packages, for other non-Bioconductor packages. So I very often use BioC-Lite to install anything, wherever it comes from. And actually, you can also use BioC-Lite to install packages from GitHub, if you know what it is. So BioC-Lite will allow you to install packages from anywhere. And so Msdata is a package that distributes some example mass spectrometry data files that I'm going to use here. And the proteomics function shows me the names of proteomics raw data that I can use. And so I'd like to use the third one to show you. So I want to have full dot names. That's true. Pattern equals DMT 11. And this is the file that I would like to take as an example. So it's a slice of a raw data file. This raw data file contains MS1, MS2, and MS3 scans. And the MS2 scans and MS3 scans contain, this is an experiment that was run with TMT 11-plex and MS3 data. It doesn't need to be like that. I just use this one because it's a recent one. And so to read this data into R, I use read Msdata, and then F, which is the name of the file. So in this case, there is only one file, but this variable can contain 10 files. And I will add one argument here. And the way I want to read this data in is on disk, okay? So it was actually pretty fast to read that raw data in, okay? These are MS1, yes? So you will get the script. I know I'm a little bit faster if I understand that I would need to give you much more time for you to do everything I do, but it's more of a demonstration, and you will get the script, so you'll be able to do it. And if you want afterwards, we can even go through some errors together. So let me rerun this again. So it's a small file. It's a slice of a full kind of, I think, 1 or 2 hour gradient run. So that file will probably be hundreds of megabytes, so it's smaller now because it's a slice. But reading it, it's instantaneous, and that behavior scales. So we have been reading hundreds of MZML files, maybe smaller ones, not with MS2 and MS3 data, but this will work. And the reason this works is that the raw data is not loaded in memory, of course. If you want to load hundreds of megabytes or gigabytes of data in memory, you need to have gigabytes of RAM on your computer. And that's generally not the case. So what we have here is now, when we type X, the name of this variable, we have a short summary of what is stored, what is contained in this X object. And that is a very new concept. These types of textual summaries, descriptions, are completely new. That's not something that we have seen so far. So far, the variables that we created were vectors and data frames and tibbles. Actually, we also stored ggplot objects in variables. Do you remember when P and then we plotted them? Okay, so these were special types of objects that were designed to contain ggplot2 visualizations. What is produced here is a special type of data structure that is meant to store raw mass spectrometry data. And so it says it's an MSN experiment data. That is its technical name. It's very, very small. It has a very, very small memory footprint. And here it tells us what we have. We have MS level 1, 2, 3, and in total we have just under 1,000 spectra in this data set. Their retention time spans from 45.27 to 47.6, and it tells us that this is when we load the data, and here's some metadata, some information that we have. So that is for my full object, but I can extract. Do you remember the square bracket operator to extract one element of a vector? Well, in this case, we have a double square bracket operator, which is something that you find in R, for example, in lists and so on. So if I have my full experiment and then I subset double square bracket operator 1, I obtain a spectrum. The first spectrum of this object, is a spectrum of level 1. It has exactly this retention time, total ion count, polarity, and so on. Let me check if my data is centrated. Ah, interesting. Okay, so that is often an important feature in your mass spectrometry data. Is your data centrated? This is something that you can ask. To your raw data. Is it centroided? We have 30 spectra that are not, 964 that are centroided. We can also ask what are the MS levels that we have, or how many of these do we have in our experiment. We have 30 MS1, 482 MS2, 482 MS3. Okay, so we have kind of full tree structure, MS1, a couple of MS2s and a couple of MS3s in this data set. And if we look a little bit more into these, we see that all this is MS level, this is whether they are centroided or not. The MS1 spectra are not centroided, the MS2 and MS3 are. This is how the instrument was set up to produce the data. So here I extracted one spectrum, and I can plot this spectrum here. So this machinery is aware that this is mass spectrometry. It's aware that what one item of this mass spec experiment is a spectrum, and it's aware that if we say plot of a spectrum object, it produces this figure. And this would also work for a spectrum of level 2 or level 3, and so on. Yes? Question? Okay. Do you have a question? Okay. So this is the kind of things that can be done with raw data. Now I wanted also to show you briefly, and I'm going to check. Yeah. what can be done with quantitative data. So I'm going to skip how to load these spreadsheets in with read MSN set2. If you type read MSN set2, you essentially pass it the CSV in and tell it which columns are your quantitative data. But I wanted to show you how these quantitative data sets look like. So what I do here on the left is that I load two other Bioconductor packages that I want to use to illustrate this. One that implements some machine learning, and the other one that provides some data associated package. And so the data functions load this data set, that's how it's called, from this package. This is like a IPRG variable or X variable. This variable has this longer name, and it's displayed here on the left. So it's an MSN set, not an MSN X, and it contains 5,032 features, in this case proteins, or 20 samples. Okay? So it's essentially a matrix, if you want, of 5,000 by 20. But in addition to that, so we have 5,032 proteins, 20 samples. In addition to that, in the MSN sets support additional feature metadata. So each protein here has another row in this associated data frame with annotation. What Go term they belong to, what description, what any other type of annotation, p-values, for example, associated for this protein, intensities for this sample, we have as much annotation as we need. Okay. This is a data matrix. Here we have the quantitative information. Here we have additional annotation for each protein has its line with annotation. And we have the same thing for the samples. Each sample here has another data frame with annotation. For example, this is a male, this is a female, female, male, maybe disease control, this is 1, this is 2, control, and so on. Quantitative information is here on its own, and it has its associated feature metadata and sample. Yes. Oh, yes, absolutely. So, for example, here we have Go terms. Here we have an NA. That information is not available. Or NA, not available. This is type was. Yes, it is not. And this is a matrix. We have numbers, and these are data frames. So, we have variables for the different observations. That's it. And so, what can we do here? Well, we can extract the expression data, the quantitative data, and, for example, pass it to boxplot to produce figures like we had yesterday these are the different samples and the distribution of intensities for these samples. And here's a final figure that I would like to show you with a, let me, going to type this here, right, so you have it. And this function would create a PCA plot and the summary of your figure, where each point here represents one single protein. So we have 5,032 points on this figure. But instead of each protein being defined by 20 values for the 20 samples, it's summarized along 2 dimensions, principal component 1 and 2, that representative of the data. And this plot is then annotated automatically, and in this case, the colors represent some subcellular annotations. Okay, so here we have subcellular clusters. Of course, this is the data about spatial proteomics, but if you had the data about something else, or you could also plot the samples and so on. So these are some kind of built-in functionalities that come of using packages that are aware of the data that you have. And I will, and finally, if you, once these packages are installed, you can always use the vignette package and specify package equals, for example, Msnbase, so any of the Bioconductor packages. And it will give you a list of all the documentation that comes with a package. Okay. So for example, if we're interested here in the vignette called Msnbase demo, we can fire it up here, and it will show up in our studio. Okay. Same documentation, it is also available online. And so I wanted to finish the course by demonstrating a last feature of R that is called R Markdown. So, are you familiar with Markdown? Is anyone familiar with Markdown? So Markdown is a markup language, so to write documents with kind of minimal markup. For example, if you want something that is written in bold, you would not write your text and then highlight it and then type Control-B or select whatever needs to be selected in Word and select bold. You would use, stars or double stars to say this word needs to be bold. And let me show you an example. So RStudio is really good for this because it provides the infrastructure to easily produce these Markdown and R Markdown documents. So if you go in File, New File, and now here you choose R Markdown. Let's give it a title, My Markdown Report. And then here I also need to specify what will be the output format. Okay? So I'm going to write this report in text, plain text. I will also add R code. But at the end of the day, when I want to distribute this report, do I want it to be in HTML or PDF? Okay. Let's use HTML here. Okay. So here we go. This is an example report, example Markdown, R Markdown document. So Markdown is this simple way to define how a text will look like. R Markdown is combining Markdown and R code. So we have a little header here that gives the title, the author, the date, and what kind of output do I want. In this case, it's HTML output. And these gray areas here, surrounded by 3 backticks, are chunks of R code. Okay. So let's compile this document. As it is, this is kind of the template document. And to do this, we are going to run knit. Okay. We were going to knit this document. That's the technical term. Oh, I probably first need to save it. So let me save my R Markdown document in my R project. Let's call it report.rmd. RMD is the extension for R Markdown. And let's knit it again. And so here it appears. So let's compare the output to the input. So we have a section that starts with these two hashtags, R Markdown. This is an R Markdown document, blah, 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 blah. When you click the knit button, and so you see that knit here is surrounded by double stars, blah, 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 blah. And then here we have a code chunk, an R code chunk that is labeled cars, and we have the command summary cars. And then including plots, a new section, and in here we have the call to plot, plot pressure, and then another paragraph. So let's look at the output. Here it is, the title, the author, the date, R Markdown, that's the first section that we had in the source document. A little text. When you click the knit button, do you remember knit was surrounded by double stars, so it shows up bold, finishing the paragraph. And then summary cars. So this is the R input, and this is the output of this command. This part was not written in the input document, was it? We only had summary cars. But knitting the document essentially means extracting all the R code that is in there, executing it, and then putting the output of that code back into the document where it's supposed to be. So this has been dynamically produced by clicking on the knit button. Next section, including plots, and here with the R. Let me change here, remove this echo equals false to equals true, and re-knit my document, so that now we have this code chunk plot pressure that is displayed, and then the figure below. Again, the figure is produced dynamically. When I click, this piece of code is executed, and it's presented here, and then the figure is inserted into the final document automatically. So here it was generated or compiled into HTML document. We can also compile it into a PDF document. You are recommended, okay. Oh, big error. Okay, something is wrong with this installation. It says that report is not found. No, apparently, unfortunately, the PDF was not generated. But believe me, it should work. I'll see if I... Okay. Some dependencies was not installed on this computer. So we will focus on the HTML output that is here. Oh, maybe we can try the Word output. Knit to Word. Yes. So it is also possible to export it to Word. And as we can see here, this was the input, and this is the output. And we should also be able to see the figure here at the bottom. Now, the reason I'm not a fan of exporting to Word is that once you have your Word document, you can start modifying it. But if you modify the document at the end, you kind of lose this reproducibility of your report. All the changes that you do in the final document, they only exist in the final document. So ideally, in my opinion, it would be much better to do more changes here and another plot, insert an R code chunk, hist R norm 100, and reknit it. So modify the source document and then regenerate a new report at the end, instead of modifying the final document. So my suggestion is that for the last 10 or 15 minutes or so before we finish, and then we will have a wrap-up session, is please try R Markdown. It's a really wonderful and powerful tools. My students, whenever we do some work together, any report they have to submit has to be an R Markdown file, and some of the kind of scientific programming course that I teach at university, the assignments are R Markdown files. And I get the R Markdown and I compile it to PDF. And if it doesn't compile, there are no marks. So but it's an extremely powerful tool, because if I get a PDF, I don't see the code. I don't know how these things were generated. Is there a bug somewhere? I actually had once a student where, I had the report, I looked at the PDF, I thought, something is wrong. But then I got back to the RMD file, and I could trace what was wrong. I could find the bug, I changed the bug, and I regenerated the PDF, and it was correct. And so the student got most of the marks because there was one bug, but that's no problem because I could identify that it was a small mistake somewhere, but the rest was correct. If I was only to look at the final result, I would just have to say, sorry, it's wrong, and you don't get your marks. So it's really, and this is an example from teaching, but imagine you do that in your research. You have your paper, and then suddenly something looks weird on a figure. What do? You need to kind of, go back through your files and my report underscore 1, final 2, and so on. Here, you always know exactly that these figures, these tables that are produced, you know exactly how they were produced. So it's really a fantastic tool, and if you don't know it, I invite you to try it out and try to adopt it. Yes?
Please scroll over to the top.
Yes?
So do you always need to have that curly bracket and R set up?
Oh, so no, this one? No, this one is optional. So what we do here is that we set specific options. This one we could forget. We could remove it. This is an option that is set, that is not important. Same thing here, one type of output is enough.
And what about the brackets below, like for cars and Regression?
Yes. So this is how code chunks are defined. 3 backticks to open, 3 backticks to close. Everything between here is R code. And then you have your curly brackets and R, because this is a code chunk with R code. That is the name of this code chunk. This is optional. And then you have other arguments that you can pass to your code chunk. For example, echo equals true means show the code here and the output if there is one. If you say echo equals false, then only the output of the code is displayed and not the code. So for example, if you have a long piece of code of ggplot2 that produces a figure, but you want your readers to concentrate on the figure and not on the code, you'd say this. And so they don't see the code, but it's there, and you know how you generated the figure, but the readers are not distracted by the code. Another one that is really useful is cache. So if you have a code chunk that takes a lot of time to calculate, you can say cache equals true. The first time you run it, the piece of code will be executed, but the result will be stored for you in a cache directory in that project. And next time you want to knit your document, it's going to check, has anything changed in here? If not, it's going to load the pre-calculated data set or output and add it for you. So that can, with big documents, lots of calculation, it can become slow. But not if you cache. Yes?
My question was about what echo.
Yes. And so, if you want to export to PDF, you need some additional dependencies, and apparently they are not installed here. But if you want to try it, and if you have issues, we can help you, of course, to get it installed. Yes?
In the Msnbase.
Yes?
So, where is the data coming from? Hyper
Okay.
IT?
Yes. So, work console. So Prolog data is a package that distributes lots of data sets. And here they are. And one of them is called Hyperlobit. This Hyperlobit is a data set that was published in a paper in 2016. It says 2015, but the paper was published in 2016. And if you want to know the details, if you type Hyperlobit, yeah, so here you have the details of that paper. And data is an R function, generic R functions, that loads pre-distributed or pre-prepared data sets. So for example, another one, data iris, which is a really well-known data set that provides kind of some morphological measurements for three iris species. So R comes with lots of data sets that can be used for testing and documentation and so on.
The express function is
yes.
within which package?
So this is the structure of an MSN set. To extract this part, we use EXPRS. EXPRS comes from Msnbase. Actually, it comes from another package that Msnbase uses because they are meant to work together, called Bioconductor. If you want to extract this part, you would use fdata. If you wanted to use this part, you would use pdata. I'll show you. EXPRS Hyperlobit 1 to 10, 1 to 4, for example. 1, 2, 3, yeah, okay. 10 first proteins in the 3 first samples. F data 1, 2, 3, 1, 2, 3. So the first annotation is the entry name, we have the protein description, and then we have the number of peptides that were identified in replicate 1, and so on. So another useful function is FR labels. That shows all the feature data that are available. So for example, we have run some classifications, so we have the SPM results, some additional annotation, SOX2 interactors, NANOP4 interactors, and so on. And so these are relevant annotations for the protein. So for example, if we calculated the p-value, we could have another column there with the p-values. these were two groups, for example, or the adjusted p-value and so on. And the last one, accessor, is p-data. That provides information about the kind of density gradient, fraction numbers, about these 20 samples. What else do we have? It was MS3, which TMT tag was used and so on. These are metadata relevant for this data set, not if you had patients, for example. The advantage of this is that you store your raw data and annotation for samples and features, where they're all well contained and kept together. Have you had to go on with R Markdown? Yeah. Well, I highly recommend it. It will. It's really a fantastic tool. And RStudio, like many other things in R, makes using R Markdown very much easier than it used to be before. Yes?
Just go back to part of the
Also, base name, the full name of that file that I loaded in is this really long path, users, presenters, but this would be different for every one of us. And so base name is a function that only returns the name of the file, ignoring the full path to the file.